Hello everyone. Let's wait a couple of minutes for people to join. Yeah, guys. So today we will be continuing the discussion we had yesterday about primes and the divisors and the sieve we had. Today we are going to cover some basic problems, some pretty standard and basic problems that it's good if you have in hand while solving problems. And then we will also discuss about a special sieve known as segmented sieve. That is also pretty standard thing, and it's good if you know this. So. Let me start with some basic problems to just get a recap of yesterday's class because today's segmented sieve definitely is based upon the sieve, right? Yeah. So let us begin with this. Let us begin with this first question. We need to find the smallest prime factor of every number from 1 to n. So let us see. Smallest prime factor. Smallest. Smallest prime factor of every number from 1 to n, and n is up to 1e6. N is up to 10 power 6. Let us begin with this question. Yeah, these are like pretty standard questions. Like whenever you are solving problems based on number theory, you think of like if somehow I had the smallest prime factor of every number, then this would help you a lot in the later steps of the solution. So these are very useful. I find them very useful. So there are like we have some other also maximum number of primes and this all this. Yeah, I'll let you know. These are very handy. So the problem statement is we want to find the smallest prime factor of every number from 1 to n, and n is up to 10 power 6. So this what we can do is the brute force method would be we just iterate over all numbers, and remember that yesterday we were checking if a number is prime or not. And while doing that, what we were doing is we were iterating through numbers from 2 to square root of n, right? 2 to square root of n, and then we were checking if it is divisible by it or not. If n for num, yesterday we were doing this, right? For standard primality test, if n is divisible by num, then we were saying that it is not a prime. So we also discussed that this loop breaks for smallest divisor of n. And we also discussed that smallest divisor is always a prime divisor. So when this loop breaks, at that time we say that smallest prime factor of n is num. Why? Because we know that this loop, because we discussed yesterday that this loop breaks when we reach the smallest prime divisor of n. So there is this one way, but this is a brute force method and it's not very timely, right? So what we can say that this is going to time out. Why? Because we have lots of numbers. For every number we have to do this. So time complexity looks like for every number we have to do root n iterations. So that is n root n kind of. Yeah. It's n root n, and for n up to 10 power 6, it would be 10 power 6 into 10 power 3, right? And that is 10 power 9. So that seems like it would take around 10 seconds. So that's pretty slow. So we can think of doing it in a bit better way. What we can do is we can think like in the sieve what we were doing. So what is sieve? It's nothing but we just iterate over divisors. We just iterate over divisors for every number, d from 2 to n, and we iterate over its multiples. So what is if we just fix a number and iterate over its multiples, and that fixed number is iterated from every number, right? We fix every number one by one and then iterate over its multiples. That is all, and and it looks like it's going to be a lot, but it's not. So it's pretty fast. So Now we are going to iterate over multiples of d. So for num is equals to 2d, for num from 2d to 2, for num in 2d 3d dot 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 up to the smallest, the closest of n, so that is n by d into d. Yeah. Okay. So this is what we did yesterday in Sieve. We fixed the numbers one by one, and then we iterated over its multiples. That's all. That is all we did in Sieve. So how is that useful? So we yesterday we discussed that using Sieve we can check if a number is prime or not, right? So do I have that code? Yes, I have. Yeah. So this was the code, right? Sieve. So in Sieve, what we did was we said that everyone is, let us assume that initially all of them are prime, and then we iterate over the fixed divisors. This D is a divisor, we iterate over every one of them. And what we were saying is, we were telling its multiples that you are not prime. We were iterating over its multiples and saying that you are not prime. Why? Because I am your divisor. I am a proper divisor of you, hence you cannot be prime. You must be composite. So I'm saying that is prime now? No, definitely not. You are not prime. So that is what we were doing, right? So yesterday we also discussed about an optimization that we need to check only for primes. We need to check this multiples only for prime. Why? Because let's say we checked for 2, we don't need to check for 4's multiples, because we don't need multiples of 4 to know that they are not prime, because they have already been told by 2, right? Because 2 already told them you are not prime. 6 has already been told that you are not prime by 2 only. Let's take a better example, 16. 16 has already been told that you are not prime from 2 only. So why we need 4 to say that again? Because all multiples of 4, they have already been covered by 2. That is why we were only iterating over multiples of prime. So if this is not prime, then we say that don't no need to tell your multiples because I have already told them. So we say continue. Okay. And now let's get back to the problem that we had. We need to find smallest prime factor of every number, right? So what is that? So this is yeah. So I'm let us maintain the array that we want. Smallest prime factor for every number up to 10 power 6. This is what we want to populate, smallest prime factor array. So yeah, so initially for every number, let us say that their smallest prime factor is themselves. Let us say that they are, because in the sieve initially we assume that everyone is prime. So if we assume everyone is prime, smallest prime factor of them would be themselves only. So this is the assumption part. So we are assuming that I am prime and I am myself smallest prime factor. So I am assigning like this. But what happens inside this loop? So what this is going to do is we are fixing a divisor, a prime divisor. When we are here, then it means that D is a prime number. Because if it has not been a prime number, we have already continued. So if D is a prime number, what it is going to do is it is going to say to its multiples that I am a prime divisor of you. So what we can do is, uh, yeah. So I am iterating over its multiples and I am going to say that I am a prime divisor of you. So what we can do is the smallest prime factor of number is equals to minimum of smallest prime factor of number, comma, this D. So why? Because let us talk about a single number. Let's say we are talking about 12. So 12 will be visited in case of 2's multiples, in case of 3's multiples, right? And nothing else. Yeah. So 12 will be visited by 2 and 3. So I am taking minimum, right? So when 2 comes, I will take minimum and I will say it to 2. And next time 3 comes, I will take minimum of 2 comma 3 and that will be again 2. So in case of 12, it worked out. Let us take example of 15. So who all will visit 15? So 15 will be first visited by when d is equals to 3 and d is a prime. So yes, this will not continue here. And I am going to iterate over multiples of 3 here. I'm going to iterate over multiples of 3 here. Uh, guys, can you hear me? Thanks, tourist. And you can see my screen also, right? Guys, please give a thumbs up if you can see my screen. Cool. So yeah, sorry about that. I'll explain this part again. Yeah. So so this is all of the things that we are going to cover today. So the first thing that we were going to cover is the smallest prime factor. So let us say that we want to find the smallest prime factor of every number from 1 to n. What we can do. So what we can do is we discuss the brute force approach where we we iterate over every number from 1 to n and we try to find its smallest prime factor separately. So every number is independent of one another and I'm trying to solve the problem independently for each number from 1 to n. So what I can do is I can simply iterate over all the numbers from 2 to square root n. This is just like checking if the number is prime or not. So what we can do is we can check if we have a prime divisor in 2 to root n because we know that when this loop breaks, that is only when we are at smallest prime divisor of n. Because we discussed this yesterday, this loop breaks when we are on the smallest prime divisor of n. So if we break it, then we say that smallest prime factor of n would be num. And if this loop does not break, then that means it's the primality check. That means that the number is prime. So we say that we n is itself smallest prime divisor. But this is not very good in time complexity because we are solving problems independently, and for every number we are going to run a loop of root n. So its time complexity is n root n, and that's around 10 power 9. So it would take 10 seconds. So this is going to get time limit exceeded. So the better way is using Sieve. So remember what we did in Sieve. We fixed the divisor from 2 to n and then we iterated over its multiples. That is all we had in Sieve. Sieve is just like fixed number and iterate over multiples. That is all we did. So this was the so in case of C, we yesterday we tried to discuss how we would find primes. Today we want to find smallest prime divisor of each number. So remember that in C, at first we assume that every number is a prime. So if we assume every number is a prime, then we also have to assume that the smallest prime factor of me is myself only. That is why I did this assumption that smallest fact I assuming I is prime. Assuming I is prime, so the smallest prime factor of I would be I itself. Okay. And what we did in the loop, we fixed a number D and we are going to iterate over its multiples. So we also discussed one optimization that if the number is not prime, for example, let's say if the number is 6, then I am not going to iterate over its multiples because because 2 and 3 have already told my multiples that you are not prime, right? Because we don't want to iterate over multiples of C again, as they have already been covered when 2 and 3 were being iterated, right? When multiples of 2 and 3 were being iterated. That's why I say that you don't need to go and say that again. Like you don't need to, 6 doesn't need to go and say to 18 that you are not prime. Why? Because 18 has already been told by 2 and 3 that you are not prime. So, so we don't need to iterate over multiples of 6. So basically, we don't need to iterate over multiples of any non-prime, any composite number. We don't have to do that. Okay. So now at this point of time, we know that D is a prime number. So what I'm going to say that uh, I will iterate over its multiples, and I am going to say to them that I am a prime divisor of yourself. So what this D is saying that I divide you. I am a prime divisor of this num. So what this num can say that I know that D is my prime divisor, and so I can take minimum. So I can take, since I need to find minimum of the prime divisors, right? For every number, I need to find the minimum of all of the prime divisors of me. So it can do is it can say that I have found another prime divisor of me. So let's take minimum of that. So it says that let us take minimum of the prime divisor. This D is another candidate of prime divisor. So I'm going to take minimum of that. And this is how we in the end, we would let us dry run it for case of 15. Yeah, we were doing dry run for case of 15. Cool. So let us do dry run in case of 15. In case of 15, who would we be iterating over? So at first 2 would be done, but 2 does not cover 15. Then 3 would be there. 3 is also a prime, so 3 is multiples would be iterated and it would cover 15. So what will happen is SPF of 15 is equals to minimum of SPF of 15 comma 3. Let me write it. SPF of 15 is equals to minimum of SPF of 15 comma 3. This happens when D is equals to 3. Next time, in case of 4, what happens? 4 is not prime. 4 is a composite number, so we are not going to iterate over its multiples. So this won't go in. Next, we have 5. 5 is a prime number. So we iterate over its multiples and say to them, I am a candidate prime divisor of yourself. Consider me for taking the minimum. So now when 15's turns come, it says that I am a candidate of you. So what 15 does is it says that, okay, I will consider you for a minimum and I take minimum among all the prime divisors that I have seen till now. So this comes in case of 5. So this is how we get SPF of 15 is equals to 3. And that is correct also. SPF of 15 is 3. So this is how we get the smallest prime divisors. So this, yeah. So basically, what the main part is, we somehow got to iterate over multiples of prime, and that is all we needed. We somehow got to iterate over the multiples of prime. So all of those multiples, I said to them that I am a prime divisor of you. Consider me while calculating minimum for yourself, and that we did inside here. So this is how we computed the smallest prime divisor of every number. Let us say that, let us say we try to print, let's say we try to print for 11, 77, let's say. So it should be 7. Let's see if this works out or not. Sieve is 1, 2, 3, up to 6 only. Okay, let's try and run this. Guys, if you have any questions in code or any part, then definitely don't hesitate and ask. Oh, of course, yeah, I forgot is prime. We have is prime also. Okay, so we have is prime also. Before going into that, let me see if you have any questions. Sir, I have a question. Find closest number to n that divides x. Is there any method to do without finding all divisors? Yes, that yeah, that part is a good one. Yeah, that's pretty simple. Let's say you want to find the closest divisor of d closest to n. Like you want to find, let's say for case of 17, you want to find closest multiple of 5. So that is 15, right? So you want to find this. So what you can do is, let me write this, n is equals to, and this is d is equals to 5. So the closest multiple of 5 to n is 15. I'm talking about the less closer, like 15, like 20 is also a close multiple, but we are not talking about the greater ones. We are talking about smaller ones. So if I want to find closest multiple of d to n, what we can do is we can try to we simply do integer division. We simply do integer division. So this we divide n by d and then we multiply it by d. So this is it. So answer is this. Answer equals to n by d into d. Let us try run it on 17. 17 by 5 into 3. I'll explain a bit like why this works. 17 by 5 is in sorry into 5. Okay, and that is 3 into 15. Integer division, remember, that is 3 into 5, sorry, 3 into 5, and that comes 15. That's our answer, and yes, that is correct also. So what I'm trying to do is, why do we do integer division? Why do we do division at all is like, I am trying to find the closest multiple, right? So the I mean the maximum quotient that we can use, right, is 3 only, because 5 into 3 gives you 17. I mean, it's pretty basic maths. I mean, I mean, I don't think I should explain it a lot. It might get confusing, but it's just simply that you just want to find the closest multiple. So you check how many multiples can I incorporate within n. You divide it by d simply, and then you see that you got 3 multiples only. Then we simply do again multiply by d. So that's how. So this is the answer, I guess. Example, it's 16 and 5, then answer should be 4. Um, mm, for 16 and 5, closest multiple of 5 should be 15 only, I guess, right? What? How is 4? I don't understand. 16's closest divisor. What is 5 here? Tourist, I think we can pick up your question a bit later. Let us continue with I mean, with the problems that we are going to discuss. We will definitely pick it up in the end. Yeah, cool. So, so yeah, we were at yeah, so we did fine, and we were running to check if 77's answer is right or not. Yeah. So, we have to make is prime also. like we did for Sieve, right? This part is same that we did yesterday, like in case of Sieve. So in case of Sieve, what I said was currently I was assuming everybody is prime. So is prime is equals to true, and this was bool. I was assuming everybody is prime. Okay. So okay. So I was checking if it is not a if it is prime or not. If it is composite, I would not iterate over its multiples. And then when I was iterating over it, I am going to say to its multiples that you are not prime. Yeah, that's what we discussed in the sieve yesterday. I'm going to say to num that D is going to say to num that you are not prime. Why? Because I divide you and I am a proper divisor of you. Hence, you cannot be prime. So is prime num is equals to false. That is all. Yeah. Let's try and run. 77's answer should be 7 because among 7 and 11, 7 is minimum. Cool. Correct. Yeah, that is fine. So, if you guys have any questions about this smallest prime factor calculation, then definitely I can pick that up right now. Uh, okay, cool. So yeah, I mean, this is usually, I'll show you how this is useful. Yeah, I mean, why this first part is useful. Yes, maybe remove that. Yeah. Okay, so before that first part, I want to cover the second part. This is also very important. This is very important to estimate how whether your things work or not. In number theory, these estimates are really important. So what I'm trying to estimate is that what is the maximum number of primes that can be present in a number up to n? So this is the question. This is important. Yeah, I'll tell you why this is also important. So now we are going to cover maximum number of primes, only primes present in n. So at first I want to tell you that every composite number, I mean you already know, every composite number can be generated from primes, can be decomposed as a set of primes, as set of primes and their powers, let's say, set of primes and their powers. This is, I mean, this is very, this is a very basic thing, but I use it a lot. I have used it a lot. This usually makes things a lot easier. So let's say there is a composite number n. So what I'm trying to say is that let's say it is made up of this like p1 to the power x1 multiplied by p to the power x2. So what is it? P1 is the prime, p2 is the prime, x1, x2 are their powers, and so on. Let me take an example. Let's say we have 12. So 12 can be expressed as 2 square into 3 to the power 1, right? 3 to the power 1, right? Because we have 2 as a prime, 3 as a prime, and power of prime 2 is 2, and power of prime 3 is 1. So this is a decomposition. Every composite number can be done in this form. So what the question is, how many primes can be there? Like in this case, for case of 12, we have 2 twice and 3 once. So for 12, we have 3 primes. Okay, so and let's take some more example. Let's say for 15, what is the answer? We have 3 into 5, which is equals to 2. So we have 2 primes. Let's say count. Count of 12 is 3. 12 has 3 prime factors. Count of 15 is 2 because it has 2 prime factors, 3 and 5. Let me write it also. 2, 2 and 3. Here we have 3 and 5. Cool. So um, now we want to find the bound for a general number. Like if I give you a specific number, then that's pretty easy. What do? You just simply prime factorize it and you just simply count it like I have done for 15. I prime factorized it into 3 into 5 and then I just counted that there were two primes. But I want to find a bound of n. Like for every number, for every number from 1 to n, what is the maximum number of the maximum number of primes a number can have? What is the maximum number of primes a number can have? For every number, among all of these numbers from 1 to n, what is the maximum number of primes a number can have? So let's say for n is equals to, let's say 10. So what is the answer for n equals to 10? So we have 1, we have 2, we have 3, 4, 5, 6, 7, 8, 9, and 10. Let's count for each of them and see what is the maximum we can get. For 1 we have 0, no primes. 2 we have 1, 3 we have 1, 4 we have 2 primes, 5 we have 1, 6 we have 2 primes, 2 and 3, 7 is a prime, we have 1, 8 is a prime, we have 2, 2, 2. So that's 3. 9 is a prime, 3 square, we have 2. 10 is a prime, 10 is not, sorry, 9 is not a prime, sorry. 9 is not a prime, it's 3 square, so we have 2 divisors. 10 we have 2 into 5, so 2 prime divisors. So I am going to say that the maximum of this is 3. So I am going to say that a number up to 10 will have maximum of 3 prime divisors. Okay, so for n is equals to 10, it was small, I simply did it manually, and I got to say that a number up to 10 can have a maximum of 3 prime divisors. This is for a number up to 10. So as the numbers become bigger and bigger, the number of prime divisors also becomes bigger. So what I'm trying to do is I'm trying to find the bound. So that the bound finding is pretty simple. So let's say that we have n. What do you think would be the maximum? What do you think would be the best way to do greedily and add prime divisors to a number? So you can see that the smallest prime is 2, right? So I would, in the greedy sense, what I would do is I would try to use as many 2's as possible, right? I would not want to use 3, because if I use 3, then the number becomes much more bigger very quickly. What I want to do is I am bounded by n, bounded by n, right? Because that's given in the question. So I am bounded by n, and I want to increase the number of prime divisors because I need to find maximum. So being bounded by n and trying to increase the maximum number of primes, I'm I my greedy sense says that use the prime 2 as many times as you want. So what I'm going to do is I'm going to use 2 again and again and again and again. I don't want to use 3 or 5 or bigger primes, because that would very quickly make my number greater than n, and I am bounded by n, so I am going to use greedy and I am going to use 2 and 2 and 2 at max and so on. Let's say f times, such that this is still less than equals to n, right? Because we are bounded by n. So this is simply 2 to the power f. This should be less than equals to n. So f is equals to around log n, log of n with base 2, log n with base 2. So this is the answer. Like the question was maximum number of primes present in n, that is log of n, around log of n. Plus minus 1, yeah, that we don't care. It's around log of n. Why we don't care about plus minus 1? Because this in general, this thing is used to estimate, like to estimate your solutions, like whether they will work, and what is the bound we have, like it in estimating time complexity and stuff. Nobody, I mean, I think nobody is going to ask exactly like given n, find maximum number of primes a number can have. Maybe in a easy problem that can have happen, but in general, this is a small thing that you use to estimate whether your solutions work or not. So like you want to know whether like let's say you are dependent upon the number of primes present in a number, and you want to estimate time complexity. So you want to estimate like how many maximum primes we can have given the constraints in the problem. So let's say we have n is equals to 10 power 6. Let's say the numbers can go up to 10 power 6, and I want to find like my solution depends upon how many maximum primes any number from 1 to 10 power 6 can have. So that I can find by log with base 2 10 power 6, and that is around 20. Yeah, that is around 20. So I can safely say that there can be at max 20 prime divisors of any number. At max 20 prime divisors of any number in the range 1 to 10 to the power 6. So this 20 is the bound that I'm going to use. So this is beneficial in the time complexity analysis and when you are discussing the solutions, right? So this was the second thing. Pretty basic. These both things are pretty basic, and they are used to solve bigger problems. We will see. Yeah. Cool. So let's see if you guys have any questions still yet. Yeah, no questions still here. So we can move to the third part. Yeah. So why I was saying why is this important? So finding smallest prime factors of every number and why this bound is important. That is because if a number, let me make another session. Yeah, another tab. So now we want to do prime factorization. We want to do prime factorization. So in this problem, we want to do prime factorization of all numbers from 1 to n. Let us begin with just prime factorization of a single number. So let us begin with prime factorization of a single number of prime factorization of, let's say, n of n. So so when you do prime factorization of n, you definitely are going to get bounds like this one. How many primes can n have, right? because you are going to do a prime factorization of n, and it's good to already know that there can be only at max 20 primes. So like this observation is a if n is equals to 10 power 6. So if you have this observation in mind, then you can definitely do. I mean, if when you are doing prime factorization of a number, then if you know that there can be only five prime factors, or let's say six prime factors, then it's a bit easy, to handle future things that you are going to do in your code, because you know that there are only five of them, so you can do a lot of stuff in the 1 second time that you have been given. So this bound is helpful in that case. So I know that there can be 20 primes at max. Cool. So I want to factorize it. So how do I go about it? So there are lots of ways we can prime factorize a number n. So let us say we use this one. Since we already find the smallest prime factor of every number from 1 to n, let us say that we found smallest prime factor of every number. As discussed earlier, every number from 1 to n. We found the smallest prime factor of every number from 1 to n. Now, this is a pretty interesting part, a neat trick, I think. So, let us say we want to factorize 12. So, how I would go about it is, I would say that I would first find the smallest prime divisor of it. So, and that is 2, and I will divide it by that number. So, then I would get 6. So, what I'm trying to do is 12 can be written as 2 into 2 into 3, right? So how I am factorizing is every time I find the smallest prime divisor and I extract it out. Then from the remaining number, and again I find the smallest prime, I extract it out. So this way, until I reach to 1, I would have extracted all of the primes the number had. So what I'm going to do is SPF of 12, that is 2. I am going to extract it out. So now number becomes 6. If I extract 1, 2 out of 12, the number becomes 6. Now I choose SPF of 6. That is again 2. So I again extracted 1, 2. Number became 3. Now I extracted smallest prime factor of the remaining number. That is 3. And that it is itself is prime. So that is 3 only. The number becomes 1. And since number becomes 1, I break. So the logic is extract smallest prime at every turn. Make the number smaller and smaller by extracting the smallest prime. Like let's take one another example. Good, let's say 27. Let's say 27, 54. Let's say 54. So the smallest prime divisor of 54 is 2. So I would extract 2 out of it, and then I would get 27. I would extract 3 out of 27, then I would get 9. I would extract 3 again because 3 is the smallest prime divisor. And why we are able to do so? Because we have populated smallest prime divisors of every number. So for case of 12, it's not like I have only populated it for 12. I have populated it for 6 already, 3 already. That is the pre-computation I am talking about. We have already done the pre-computation. So that is why we can easily do this. And what would be the time complexity of it? It's only 20 operations at max. Why? Because we know already that there can be only 20 primes, and in every turn we are extracting one prime out of it. So this can only go up to 20 operations at max, right? So this is how you just estimate, like if somehow I have this smallest prime factor of every number, I can in at max 20 operations, I can find the prime divisor of any number if you give me of any number. So and how much time did it take? Let us also take that into consideration. Time complexity of estimating of finding SPF table. SPF table. So what was the time complexity? It was like Sieve. So let's check that again. Yeah. So this is n. This is n. This is n, but inside, if it is prime, then we are iterating over its multiples. So it's like n by 2 plus n by 3 plus n by 4. Why n by 2? Because for every number from 1 to n, there are n by 2 multiples of 2. Numbers from 1 to n, there are n by 3 multiples of 3. So that is why. So this loop runs n by d times, right? So we have n by 2 plus n by 3 and not n by 4, directly n by 5, because we are not iterating over 4. We discussed that earlier. We are iterating only over multiples of primes. So we have n by 2 plus n by 3 plus n by 5, so on. And that I remember yesterday we talked about, that's n log log n. So that is n log log n. So this was there, and then let's say we for let's say we wanted to find out about one n, then we know that it's again another log n. Oh, sorry, not here. Plus log fn, because in this case we wanted to find a number of primes present in only n, so we know that that is bounded by 20, and in each term we are extracting one prime out of it, so we know that at max log n operations are going to take. So this is the time complexity. Seems pretty nice. Yeah, for n is equals to 10 power 6, definitely it would work. So let us expand our question to not just finding the number, not just find. Oh, this wasn't in the case. Yeah, this one second. This one here. Yeah. Yeah, so time complexity of SPF table was this, and yeah, and finding the prime factors of n, that was 20 steps we needed at max. So this was it. So now we can expand our question to not just prime factorize a single number, but we can prime factorize all of the numbers from 1 to n. Let's see how much time that would take. So we want to prime factorize all of the numbers from 1 to n, right? So, what can we do? I mean, we can simply use this technique that we had for one number, and you can iterate it, you can apply it on all of the numbers. So, this pre-processing is common for every of them, right? This pre-processing part is common. This is the maximum number of operations that we needed for one number. Since there are n numbers, I'm simply going to multiply it by n log n. This is a solution where what I do is I iterate over all numbers and I run this thing that I did. For 12 I do this, for 13 I do this, for 15 I do this, so on. For every number I do this, and I know that any number if I take, that is going to be finished up in 20 operations only, log n operations only. So we would be needing one n log n extra for after the pre-processing of smallest prime factor table. This is how much time we need to process all of the prime numbers of all of the numbers from 1 to n. So this is the time. This is also a pretty neat time complexity. This is definitely going to work. Let's find out how many operations it is. For n is equals to 10 power 6. That is 10 power 6 log n power 6 multiplied by log of 20. First log n is 20, then multiplied by 10 power 6 into log of n, that is 20. So that is 10 power 6 into log of 20 is 5, plus, oh sorry, this is plus, 10 power 6 into 20. So that becomes, let's say 10 power 6 common, that becomes 25 into 10 power 6 into 25. And that becomes like 2e7 operations around. 2e7 operations. 2.5 to be exact. 2.5e7 operations, and definitely, yeah, it works in 1/4 of a second. Yeah, because assuming we take 1 second for 10 power 8 operations, this works in 1/4 seconds, and that's pretty fast. So, can we do any other optimizations like I don't know. Let us see. Let's not optimize. Let us write code for this. Yeah, that is. I think that would make it more clear. So this is not sieve now. This is process SPF table. So this is how we process the SPF table. We find the smallest prime number, smallest prime factor of every number. So what I'm going to say is that process SPF table beforehand for every number. Now I'm going to say that process primes, prime factors, prime factors for every number. Hmm. Okay. So I'm going to check how much time does it actually take. So process prime factors. We take n, and what we are going to do is we are going to do that thing that we discussed for 12. We are going to do it for every number. For int I is equals to 1, I less than equals to n. This is the I have fixed. Let's yeah, that is I, and let's maintain a vector like because there are multiple primes, we have to maintain a list or vector or anything, right? So for every number, so primes list, let's say primes list for every number. Cool. So what does primes list of, let's write that for, that would make it much clearer, I think. Primes list of simply take one example. Prime list of 12 would be 2 comma 2 comma 3. Yeah, that would be the prime list for 12. So, and similarly we have prime list for everyone. Yeah. So that I want to process. So what I'm going to say is that I'm going to, let's say, we take another variable, copy it, and then I'm going to say that while d is not equals to 1, while the number is does not become 1, what we are talking about is this thing. Where is it? Prime factorization, right? Yeah, while 12 does not become 1, we extract smallest prime again and again and again, and we push it to the list and we reduce the number again. So what while d does not become 1, I am going to say that primes list primes list of I has another prime. And what is that? That is the smallest prime factor of d. Okay. So what I'm extracting smallest prime factor of d and pushing it into the primes list of I, because we are factorizing I only. And then I am extracting that smallest prime factor out of d. So we divide by d is equals to d divided by SPF of d, right? So what does this mean? Let me take example of 12 only. So for case of 12, what we do is we push 12, we push 2 in the list, we reduce 12 by 2. 12 becomes 12 by 2, and that is 6. So 12 becomes 6 now. Next time, what would happen is 6 has the smallest prime factor 2. 2 would be pushed, and 6 would be reduced to 3 by this statement. What will happen next? 3 is still not equals to 1. We push smallest prime factor of 3. Smallest prime factor of 3 is 3 only. We add it to the list and we reduce it to 1. 3 divided by 3, that is 1. And then we break out of the loop because we have while loop. So this is how we, and we can just simply, let's say we want to check for, let's say 54 only. So prime in for for prime in primes list of 54, let's see if we get the primes appropriately or not, if this code is working or not. Prime, okay, cool. So let's compile it and run it. Let's see. Yeah, cool. We have 2333, is that right? Where did I do it? 54 did I do? I thought I did 54. Okay, we can do that again. Yeah. For 54, first smallest prime factor is 2. Then we have 54 becomes 27. 27 we have 3, that becomes 9. Then we have 3 again, it becomes 3. Then we have 3 again. 2, 3, 3, 3. That's right. Yeah. So this is yeah, how we do that. Cool. So yeah. So what there is one interesting thing I want you to note, that is about the time complexity. Like here we discussed that time complexities of smallest prime factor is n log log n. That part is correct. And then we said that we are going to be doing at max 20, at max log n operations for every number. So our time complexity is n log n, right? But it actually is n log log n. I'll tell you why it is actually n log log n. Because it is why, because we are not going to iterate over all login times every time, right? For example, for a prime number, it just takes one operation, not 20 operations, right? For let's say 15, it takes only two operations and not 20 operations. So how do we, and it's not like that we are wasting any operations, right? Uh, this loop would break out of it in one operation only if D is a prime, right? If D is prime, then at the first iteration only, we reduce it to one and we break out of the loop. So what actually we want to do is we want to analyze how many total operations actually we are taking. The bound n log n is a quite a high upper bound, but we know that every number does not take 20 operations to get reduced to one. Prime numbers get take only one operations. So we want to find the actual total number of operations that we are taking. So what we can do is we can, I mean, you can estimate it by doing operations plus plus here, because this is the innermost operation that we are doing. This loop, inside of it, we can do operation plus plus, and then we can see why it is not coming to be of order n log n, and it is coming to be of order n log log n. Another thing we can do is we can analyze it ourselves only. So let me show you how it is n log n. So it's just like in Sieve, we fix a prime divisor instead of iterating over prime divisors of a number. We fix a prime divisor and see how many, in how many numbers, in how many lists does it go into. So let's say we talk about 2. So where in whose list does 2 go to? So in case of 4, yes, we have a 2 there. In case of 6, we have a 2 there. In case of 8, yes, we have a 2 there. In case of 7, we don't have a 2 there. So 2 goes in around n by 2 elements. So 2 is pushed into around n by 2 lists, n by 2 primes list here. Like in case of 2, 4, 6, 8, 12. Inside of those lists, we find a 2 present there. Yeah. So 2 is present in around n by 2. Did I say that? Yeah. 3 is present in around n by 3 elements. 4 is present in around, no, 4, not 4. 5 is present in around n by 5 elements. N by 5 elements, right? Yeah. I guess there is one thing still to note that we just do not care about distinct prime divisors here. Yeah. We are talking about, like, let's say in case of 8, it's not that 2 is just pushed once. It's pushed again also, right? It's pushed twice also. Yeah. So I guess that part is incorrect. Like for 8 case, we have 2 pushed thrice. So if we count like this way, n by 2 pushes, then n by 3 pushes, then n by 5 pushes, then so on, then the bound comes n log n, but that is not correct because here I am assuming that 2 has been pushed only once. But it's not the case. For eighth case, we have 2 pushed thrice. So so that part is there. So how do we correct that? How do we correctly analyze it? So 2 is pushed into n by 2 times. 4 is pushed 4 is pushed, yeah, n by 4 times. 8 is pushed n by 8 times, yeah. So not just checking about primes, but we have to check about we have to add for powers of primes also, right? So like for a prime p, for case of 2, we have to not just only add n by 2, because we are not just because in case of 8, it is being pushed 3 times. First for 2, then for 4, and then for 8, because it has three twos, right? That is why. So that is why we need to add n by 2, then we also need to add n by 4 also. We also need to add n by 8, and then we also need to add n by 16 also, and so on. So all powers of 2 we need to add. So looks like this is going to be tricky. Let's do that stuff only. We do operations plus plus, and let's see if this is indeed correct. We have operations equals to 0, operations plus plus, and let's see how much operations does it take. And we will see if this is around that or not. Cool. So operations, yeah. Let's see. Yeah, I did it inside it. Correct. That's fine. 3626637. These are the operations that I done. So let's remove this. This is getting messy. 1, 2, 3, 4, 5, 6. This is 3, 6 only. Yeah, this is 3, 6. Looks like it's around order of n log n is still. Yeah, right? Because n log n is around, how much is n log n? We have 10 power 6 into 20. So it should be around 2v7 order, right? 10 power 6 into 20, that is 2v7. But this is coming to be much less. It is coming to be 3e6. So what is n log n? That is around 5e6. Yeah. So for n log n, it would be around 5e6, because log of 20, I am taking 5, but it's maybe 4 or 5. So let's take it 4. So it's much closer to n log n. So the time complexity is still n log n. I think, yeah. So we can prove that mathematically, but it might take a while. Like we have to do some mathematical series summation, like not just, I mean, in case if we have to find distinct primes, then that thing we earlier did, we like iterating over primes, adding n by 2, then n by 3, then n by 5, then n by 7. That part is okay for that. But here we know that we cannot just add 2 only once. In case of 8, we have to add it 3 times. So how do we do that? We have to add it in case of 4 as well, because in case of 4, we have one more prime. In case of 8 as well, we have to add that. In case of 16 as well, we have to add that. So looks like we have to solve some GPs and then sum that up. Looks like some mathematical uh, more mathematics would be needed there, so we can avoid that right now. So looks like complexity is still n log n only. So earlier we were saying that complexity is n log n plus n log n plus n log n, but this is still n log n only. So we can say that, and n log n plus n log n, that's n log n. So n log n we have. Cool. So yeah, this was about how much did we cover? We talked about smallest prime factors. and the maximum number of primes we know it's order log n. We've prime factorized everyone. So yeah, this technique is important. I want you guys to remember the technique that we prime factorized it. We first find the smallest prime factors, and then we extract the smallest prime factor one by one, one by one. Like in case of 12, remember just this example. That would be, I think, easy to remember this technique by. We extract two out of it, we extract three out of it, and we extract. I mean, we first extract two, then we extract two again because like this you can, yeah, you can remember it this way. This is how we prime factorize. So once a number is prime factorized, there is a, I mean, you have a lot of control over that number. Like there is a, I mean, you have a lot of power. Like you know that it has only 20 prime divisors. You know the exact prime divisors. You know the exact powers of those. There is a lot of thing you can compute about that number once you have a prime factorization of it. Cool. So next is this. This is a bit different one. Huh? I want to find number of divisors of each number. Cool. So I want to find number of divisors of each number. So let us close these. These are a bit different. These were related to primes and prime factorization. So let us count. Let us see about divisors. Let us say the problem. I want to count number of divisors. Number of divisors of each number. Number of divisors of each number from 1 to n. Cool. So how do we do that? I just want to find the number of divisors of each number. Okay. So depends upon n, of course. Depends upon n. Like I can't solve it for everything. We have to do it. Let's say we have n is equals to 10 power 6. We have n up to 10 power 6. Okay. Let's frame it into two problems. Count of number of divisors for a specific number of n, and then for all of the numbers from 1 to n. Let us begin with this case. We have to find the number of divisors of a single element, single number we are given. What we can do is first we have to observe that divisors come in pairs. What I want to say is that let's say we have 12. Then if 2 is a divisor, we know that 6 is also a divisor. 12, we have 2. So we discussed it yesterday also. If D is a divisor, then N by D is also a divisor. So you can say the divisors come in pair except for perfect squares. Let's say for 9, we have 3 as a divisor. So 9 by 3, 3, that's same. I mean, it still holds that if D is a divisor and N by D is a divisor, it still holds, but they are not distinct here. So we have to remember this case because we want to count the divisors and we cannot count 3 again, right? So let's say about 12. Let's say for 12 we have let's say we calculated brute force way. We have 2, we have 3, 4, we have 6, we have 12. Oh, sorry, one I forgot. One we have, yeah, 1, 2, 3, 4, 6, 12. These are the divisors we calculated manually. Cool. So brute force way is iterate over all elements for number from 1 to n. If n is divisible by that number, we say that got a divisor, divisor plus plus, divisor plus plus. I got a divisor, divisor plus plus. That is the brute force way, and it takes around order of n time. And let's say if the number is up to 10 power 12, so we won't be very happy about this. It would take a lot of time. So what optimization can we do? The thing that we discussed here. We have a divisor. The divisors come in pairs. We have D, we have n by D. So what I am going to do is I'm going to find a smaller one of them, and I'm going to just assume that there exists another divisor for that. I mean, definitely, I'm not going to assume. I know that there exists another divisor of that. So for small d, I'm going to assume that there n by d exists, and I'm simply going to increase my counter by 2. Okay, so let's say I'm going to increase my counter by 2 for the smaller one of these. So I mean to say that let's say for d is equals to 2, we have divisor d 2 comma 6. So what I'm going to see that when I find 2, I'm going to increase my counter by 2, not by 1, by 2, because I know that 6 exists. But we have to take care that when 6 comes, I don't add it again because I have already counted it. So the special thing about this is that the minimum of d comma n by d, that can go up to root n only. That is we discussed yesterday also while we were factorizing prime. This square root n thing comes up a lot in this scenarios because we know that if we have a small divisor, then there is a bigger divisor also. If we don't have a small divisor, a bigger divisor cannot exist. Just like in case of prime we did. So what I mean to say that I want to I want to consider only D's where this is the minimum one. Like I have D is equals to 2, so I will consider it because corresponding n by d 6 is bigger than me, is bigger than me. So I want to prevent double counting. So what I'm going to do is I am going to run this loop, exact same loop, but not for every number from up to n. I am going to do it up to square root n. Why? Because I am going to increase the divisor count by 2, because I am going to what I am iterating over smaller divisors and assuming that there is a bigger divisor also, and I just count it. I am not going to iterate over it. I just count it. So this is how we do it. And of course, we have a special case here. If n is a perfect square, that means in case of 9 we counted it. If n is a perfect square, that means in case of 9 we have counted it twice. So we decrease our answer by minus 1 by 1. Divisor minus equals to 1. Yeah. So let us dry run this on case of 9 only. So for number from 1 to square root of 9, that is 3. So we iterate over 1, 2, 3. 1 divides n, yes. So we increase the counter by 2. 2 divides n, no. 3 divides n, yes. So we increase counter by 2. So we have 4 in the end. But n is perfect square. So we decrease the divisor count by 1. So in the end, the final result is 3. So for n is equals to 9, we have answer as 3. Answer equals to 3. Let me check if you guys have any questions. Yeah, cool. Okay, no. So, yeah. So this is the what is the special thing that we are using here? It's that the divisors come in pairs. There is a lot of observation you can do here. First observation is you can see that divisors come in pairs, and it was fine to iterate over up to root n only, and corresponding divisor was counted automatically, because I know that there is a corresponding divisor for 2, there is a corresponding divisor for 3. Like in case of 12, if 3 is there, then we know that 4 is already there. So why go on to 4? Just count 4 in 3 only. So this is exclusive, like divisors are in pairs, so they are exclusive to one another. So what we can say that we had just to iterate over root n. Another observation is that the divisor count is bounded by root n only. Like the maximum number of divisors of a number, there can be up to 2 root n only. 2 root n. Because we know that even if every number from 1 to square root n divides n, we are going to do plus 2 for each of them, and that gives us a bound of 2 root n. That is also a pretty important observation. Number of divisors, number of divisors of a number up to n is bounded by root n, order of root n. This is also very important in case of analysis. In number theory problems, we have to see if our solutions are fast enough or not, and our solutions are only fast enough. I mean, sometimes our solutions are fast enough, we don't even know it. Therefore, we have to do analysis. We have to do like how much this can go to, how many operations this can happen. Like you can see that, yeah. I mean, these bounding is very important. Like maximum number of primes that we did, like log n number of primes. Then this thing again, number of divisors of a number. They can go up. They can be around O of root n only. Maybe they can be even bounded some more. Maybe it's less than root n. Maybe it's around cube root n, or maybe